Carbon is an essential element of all organic compounds. Carbon, which is tetravalent, has the ability to successively bond with other carbon atoms to form long chains or rings. The property of self-linkage of carbon atoms is known as catenation. Carbon also forms covalent bonds with hydrogen, oxygen, nitrogen, sulfur, and halogens. These carbon compounds are known as organic compounds. And the branch of chemistry that studies the formation and properties of organic compounds is known as organic chemistry. Organic compounds form the basis of life. For example, deoxyribonucleic acid or DNA is made up of sugar like 2-deoxyribose and nitrogenous bases. In blood, muscles, and skin. Organic chemicals are also present in clothing, as in nylon fabric. In fuels, as a mixture of C7 to C9 hydrocarbons. In polymers, like polyethylene. In dyes, such as bromophenol blue. And in medicines, such as aspirin. In 1780, chemists discovered that organic compounds can be obtained directly or indirectly from plants and animals. While inorganic compounds are obtained from non-living resources such as minerals and rocks. In 1815, Berzelius, a Swedish chemist, suggested a theory which is known as the vital force theory. In his theory, he stated that organic compounds are produced only under the influence of some mysterious force existing in the living organisms. However, in 1828, Friedrich Wöhler, a German chemist, rejected the vital force theory. Wöhler synthesized an organic compound, urea, by heating an inorganic compound, ammonium cyanate. Later in 1845, Kolb synthesized acetic acid from purely inorganic compound. And in 1856, Berthelot synthesized methane from an inorganic compound. Thus, this led to the end of the vital force theory. A few years later, scientists found out that natural and synthetic organic compounds essentially contain carbon and hydrogen. And at times, they also contain other elements such as oxygen, nitrogen, sulfur, halogens, and phosphorus. Organic compounds made of only hydrogen and carbon atoms are known as hydrocarbons. All other organic compounds are considered to be derived from hydrocarbons by replacing one or more hydrogen atoms with atoms of other elements. Thus, organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. The tetravalence of carbon can be explained from its valence shell electronic configuration. We know that the outermost shell of an atom is known as the valence shell. Electrons present in the valence shell, that is, valence electrons, take part in the chemical reaction. The electronic configuration of carbon is 1s2, 2s2, 2px1 and 2py1. This means that the valence shell has only 4 electrons. All elements tend to complete octet in their valence shell to become stable. Since carbon has 4 electrons in its valence shell, to complete its octet, the valence electrons of it form 4 covalent bonds with atoms of other elements. This characteristic of carbon atom, by virtue of which it forms 4 covalent bonds, is called as tetravalence of carbon. Thus, carbon forms a wide range of compounds. In this example, methane is formed by sharing 4 electrons of carbon with 4 hydrogen atoms. The formation of molecules and their shapes can be explained by considering the hybridization of s and p orbitals respectively. Now, let's look at how hybridization explains the shape of ethene molecule, that is, C2H4. In ethene, each carbon atom undergoes sp2 hybridization. 2 sp2 hybrid orbitals of each carbon atom overlaps with each of the 1s orbitals of 2 hydrogen atoms to form 2 sigma bonds respectively. The remaining sp2 hybrid orbital of a carbon atom overlaps coaxially with a similar sp2 hybrid orbital of the other carbon atom to form a strong carbon-carbon sigma bond by sp2-sp2 overlap. The unhybridized or pure 2pz orbitals of both the carbon atoms overlap laterally to form a weak carbon-carbon pi bond by pp overlap. Pi bond doesn't account for the shape of the molecule. All the 6 atoms forming the sigma bonds lie in one plane, and the pi bond lies perpendicular to the plane. Thus, the shape of the molecule is trigonal planar. Hybridization influences bond length and bond strength in organic compounds, which means that these parameters do influence the shapes of molecules. Among sp3, sp2 and sp, in an sp hybrid orbital, the s character is maximum, that is, 50%. Greater is the s character, closer is the orbital to the nucleus, and hence higher is the electronegativity of that carbon. Also, these effects result in shorter hybrid orbital, shorter bond length and greater bond strength of the bonds formed by sp hybrid orbital. In sp2 hybrid orbital, the s character is 33.3%, and in sp3 hybrid orbital, the s character is only 25%. Hence, the bond length is more in case of the bonds formed by sp3 than sp2 hybrid orbitals, and least in case of the bonds formed by sp hybrid orbitals. In sp2 hybrid orbitals, the s character lies between sp3 and sp hybrid orbitals. Hence, its bond strength and bond length is intermediate between them. Let's compare the CH bond lengths and the bond strengths in ethane, ethylene, and acetylene. Thus, bond strength of sp hybrid orbital is greater than sp2 followed by sp3 as shown here. And the bond length of sp3 hybrid orbital is greater than sp2 followed by sp as shown here. Thus, the greater the s character, the greater is the electronegativity. Sp is more electronegative, followed by sp2 and sp3. Now, let's look at certain characteristic features of a pi bond. The bonds formed by lateral overlapping of pure p orbitals are known as pi bonds. Let's look at the pi bonds in ethylene. Here, the pure p orbitals of both the carbon atoms, which are mutually parallel to each other, form a pi bond that is perpendicular to the plane of the molecule. Rotation of C around the double bond is strongly restricted, as the pi bonds prevent the free rotation around the carbon-carbon bond. In a pi bond, the electron charge cloud is present above and below the plane of the bonding atoms. Hence, these electrons are more exposed and susceptible to attack by electron-seeking reagents. In general, pi bonds provide the most reactive centers in unsaturated molecules. The pi electrons are more tightly held by the carbon atoms in acetylene, as the carbon atoms are sp hybridized compared to the pi electrons of ethylene, in which the carbon atoms are sp2 hybridized. Hence, acetylene is less reactive than ethylene. A chemical formula which represents the arrangement of atoms in a molecule is called the structural formula of a molecule. The various structures of organic compounds can be represented by 4 different ways. They are Lewis structural formula or dot structural formula, dashed structural formula, condensed structural formula, and bond line structural formula. Let's first look at the Lewis structural formula. The Lewis structure is named after the scientist Gilbert N. Lewis. In Lewis dot structure, a pair of electrons forming a covalent bond is represented by using a dot or cross. However, the Lewis dot structure can be further simplified by representing a pair of electrons by a dash. This simplified representation is called dash structure. Thus, a pair of electrons forming a single covalent bond is represented by a dash. A double covalent bond is represented by a double dash, and a triple covalent bond is represented by triple dash. Organic compounds containing heteroatoms with lone pair of electrons are represented by a pair of dots on the respective heteroatom. This structure represents the bonding between atoms in a molecule and also shows the presence of lone pairs present on the atoms, if any. This structural formula shows the arrangement of atoms and the type of bonds present between the atoms in the molecule. Here's the dash structural formula for ethane. In ethane, 2 atoms of carbon are attached to each other by a single covalent bond, and all carbon-hydrogen bonds are also single covalent bonds. In ethane, 2 atoms of carbon are connected with a double bond, and 2 hydrogen atoms are attached to each carbon by a single bond. In ethyne, 2 atoms of carbon are connected with a triple bond, and 1 hydrogen atom is attached to each carbon by a single bond. In methanol, carbon is attached to 3 hydrogen atoms and 1 hydroxyl group. 2 lone pairs of electrons present on the oxygen atom of hydroxyl group are represented as shown here. Now, let's look at the condensed structural formula. In a condensed structural formula, some or all the dashes that represent covalent bonds are omitted, and the number of identical groups attached to a carbon atom is represented by a subscript. Thus, a condensed structural formula is an abbreviated form of dash structure. The condensed formula of ethene, ethine, and methanol are represented as shown here. At times, the formula is further condensed by enclosing the repetitive structural unit within a bracket and placing an integer as a subscript, indicating the number of times the structural unit is repeated. In this case, CH2 is put within brackets and has a subscript of 6, indicating that the structural unit CH2 repeats 6 times. Finally, let's look at the bond line structural formula. A bond line structural formula is a short and simplified method for representing an organic compound. In this method, carbon-to-carbon bond is represented by lines drawn in zigzag fashion, represent carbon-to-carbon bonds, and line terminals generally represent methyl groups if they don't have a functional group, whereas the line junctions represent the carbon atoms attached to appropriate number of hydrogen atoms required to satisfy the valency of carbon. If any heteroatoms are present in place of hydrogens, they are specifically written by using their symbols as shown here. Let's consider the dash structural formula of 3-methyl octane. Now, let us represent the bond line structural formula for this as shown here. Here is the condensed structural formula and the bond line structure formula for 2-bromobutane. Cyclic compounds are represented by polygons. In a polygon, the corners represent a carbon atom and the sides represent a carbon-carbon bond. Symbol of atoms other than carbon and hydrogen are shown on the structure. Organic molecules can be represented by using the solid and dashed wedge formula. This is a 3-dimensional structural representation of an organic compound. This formula can be represented on the paper by using 3 conventions, that is, a dash, a solid wedge, and a dashed wedge. A dash is used to mean that the bond is in the plane of the paper. A solid wedge means that the bond is projecting out of the paper and is towards the observer. A dashed wedge is used to mean that the bond is projecting out of the paper and is away from the observer. The 3D image for the methane is shown here. 3-dimensional molecular models are used for better visualization and perception of the shapes of organic compounds. There are 3 types of molecular models: framework model, ball and stick model, and space filling model. In the framework model, the atoms are not shown. Only the bonds connecting the atoms of a molecule are shown. This model is used to study the patterns of bonds and does not consider the size of the atoms. In the ball and stick model, both bonds and atoms are shown. The balls represent atoms while sticks represent bonds. Compounds containing double bond, as in ethene, are represented in a different way. In place of a stick, a spring is used to represent the double bond. Hence, this type of model is called ball and spring model. Another type of molecular model is space-filling model. The relative size of each atom is based on van der Waals radius. That is, the volume occupied by each atom is shown. Bonds are not shown in this model. To simplify and systematize the study of organic compounds, they can be classified on the basis of their structure as open chain or acyclic compounds and closed chain or cyclic or ring compounds. Open chain compounds are also known as aliphatic compounds. The term aliphatic is derived from Greek word alipha, meaning fat or oil. The compounds in this class are derived from vegetable or animal fats. Open chain or acyclic compounds are compounds in which carbon atoms are linked by straight or branched chains. Some examples of straight chain compounds include butene, butyne, pentyl alcohol, acetone. Some examples of branched chain compounds are isobutane, isobutylene. In a cyclic or ring or closed chain compound, the carbon atom and any other atom, if any, are joined together to form a closed ring. For example, in cyclohexane, 6 carbon atoms join together and form a closed ring. Cyclic compounds can be further classified as homocyclic or carbocyclic compounds and heterocyclic compounds. The word homo means same. Thus, homocyclic or carbocyclic compounds are those in which the ring consists of only carbon atoms. For example, in cyclohexane, the ring consists of only carbon atoms. The word hetero means different. Heterocyclic compounds are those in which the ring consists of carbon atoms. As well, the other atoms like sulfur, oxygen, or nitrogen. Homocyclic compounds can be further classified as alicyclic compounds and aromatic compounds on the basis of their characteristic properties. Homocyclic compounds, which resemble aliphatic compounds in their properties, are called alicyclic compounds or aliphatic cyclic compounds. An alicyclic compound consists of a ring which has only carbon atoms. For example, cyclopropane, cyclobutane, and cyclohexane. Aromatic compounds are benzene and the compounds that resemble benzene in their behavior. Aromatic compounds can be further classified as benzenoid compounds and non-benzenoid compounds on the basis of the presence or absence of benzene ring. Aromatic compounds containing isolated or one or more fused benzene rings and their functional derivatives are known as benzenoid aromatic compounds. Benzene is the parent compound in benzenoid derivatives. A non-benzenoid compound is one that does not contain a benzene ring. For example, tropolone as shown here. There is another class of aromatic compounds called heterocyclic aromatic compounds. These compounds contain heteroatoms such as nitrogen or sulfur or oxygen in addition to carbon atoms in the ring and resemble benzene in their properties. For example, pyridine, thiophene and furan are heterocyclic compounds containing heteroatoms, sulfur and oxygen respectively. The other way to classify the organic compounds is on the basis of functional groups. A functional group is an atom or a group of atoms present in a molecule, which determine its characteristic properties. For example, hydroxyl group and carboxylic acid group is the functional group of alcohols and carboxylic acids respectively. Organic compounds can also be classified on the basis of homologous series. The successive members or series of organic compounds with a characteristic functional group having the same general molecular formulae and differ by CH2 unit form a homologous series. The successive members of a homologous series are called homologs. For example, the homologous series of alkanes are methane, ethane, propane, butane, and so on. The successive members such as methane and ethane are called homologs.